This is the second video of our Chapter 6-7 AP exam review. We'll take a look at Chapter 7 in this video, a few of these questions. Chapter 7 is about the periodic table. So there's a lot of things that we talked about in terms of size and ionization energy. So why don't we take a look at a few of these. Why don't we take a look at 21 and 22, and I'll let you do the first few. So 21, take a look at that one. Which of the following lists oxygen, fluorine, sulfur in order of increasing atomic radius? Now, if you recall, the general trend on the periodic table is that radius increases, or size, you can say, increases as you go to the bottom left. So your smallest element of all is helium. Helium wins as the tiniest element of all. So since you have sulfur, oxygen, and fluorine, fluorine is in the corner here, right before the normal gases. And then oxygen is a little earlier, and then sulfur is right below oxygen. So you'll see that sulfur is the biggest, and then oxygen smaller, fluorine is the smallest. So sulfur should be the biggest, which gets us this one, and then oxygen, and then fluorine. So E would be the answer. Now, there are no exceptions to the radius trends. So size has no exceptions. No exceptions. Exceptions to trend. Now, there will be exceptions, if you recall, for ionization energy, which we'll take a look at, as well as all the other periodic trends like electron affinity and electronegativity. So the others are ionization energy, electron affinity, and electronegativity. These are the other trends. So you can say yes exceptions. And by yes exceptions, what we mean is as you, in general, for example, increases and then all of a sudden goes down and then it keeps increasing. So that's the idea for these exceptions. All right, let's take a look at 22. Now 22 says, which of the following correctly identifies which has the higher first ionization energy, fluorine or argon, and supplies the best justification? Now if we take a look, both chlorine and argon are actually right next to each other. They're in the second group right here. So here's chlorine. We put chlorine right before fluorine, and then argon is right next to it. So we know ionization energy increases going this way. So IE increases as we go up, which means argon should have the higher ionization energy, and it does. So argon has the higher ionization energy, which means chlorine is out. The question is which best identifies the reason. C says argon because it's completely filled valence shell. Now this is true. Valence electrons, remember, increase this way. So fluorine has 5 valence fluorine has 7 valence electrons, 5 in the S or in the P subshell. All right. So argon does have a full, all 8 of its valence electrons are complete. However, that's not the best answer. The best answer, if you remember, is this magical word, effective nuclear charge, also called ZEFF. Z means nuclear charge, number of protons, which pulls the electrons toward the nucleus. So anytime you see this explanation, you should always be pulled toward it, attracted toward it. This is the best explanation, so D. And we'll take a look at this again, this idea of effective nuclear charge. All right. Incidentally, most of the exceptions, which we'll see here, occur, remember, between the blocks, so between the S and the P block, and then halfway through the P block. That's where you get your exceptions. So here, your exceptions show up. And we'll take a look at a question or two that actually discusses it. I'll take a look at 24. 24 will actually discuss it somewhat. Okay. This is actually somewhat of a different question because it takes a look at the first 5 ionization energies of one element, of a second period element, and they're listed on the right. You'll notice that, so we're removing the electrons from one element. Now, every time you remove an electron from an element, it gets tougher and tougher and tougher to remove it because the rest of the electrons pull closer. So here you have an atom, and if you remove one of its electrons, what happens is the electrons are pulled closer to the nucleus, the rest of the electrons, and it becomes smaller. And this is always true. So, but you'll see that the increase is very big as you go from the third to the fourth. So after you remove 3 electrons, removing the 4th one is extremely difficult. Now this is true because we are going between either subshells or shells. So let's visualize really quick what these would look like. So if you take a look, this is for the second period element. So we're right here, second period. First period is just hydrogen. So you have lithium, we have beryllium, then we have boron, carbon, nitrogen, oxygen, fluorine, and then we have our noble gas, neon, right here. So our two options are boron or nitrogen. So it's either this guy or nitrogen. Now, with nitrogen, you see that you can remove the first 3 electrons and you're done with the p subshell. With boron, you remove the first 3 electrons and you're done with the second energy level. So because the change is so big here, I mean a good 6-7 times, really big order of magnitude, most likely this is due to a new shell being created. Not a new subshell, but a new shell being accessed. Or not new shell, but the shell being completely removed. So in fact, this would represent boron. So its first electron's removed, which takes 801 kilojoules. Second electron, more as expected. Third electron, even more as expected. But then it becomes like helium, like this element right here. And it'll be very difficult to remove its fourth electron. So the better answer is actually boron. So boron, because it has 3 valence electrons. It does have 5 core electrons. It is true it has 5 core electrons, but that's not the explanation. The 3 valence electrons is the explanation for boron. So think through that one. That one actually is a good one to think about. There's a few questions in the same category a little later on as we look at this. Let's take a look at one question on the back, or on the next page, rather. Let's do 31. A very similar idea. This connects, 31 connects size and ionization energy. So let's look at 31. So the table on the right shows the first ionization energy and atomic radius of several elements. Which of the following best helps to explain the deviation of the first ionization energy of oxygen from the overall trend? Again, we're looking at the same period. So we're looking at, here's boron, carbon, oxygen, nitrogen, fluorine, and neon, our noble gases. So we're actually looking at the P block, just the P block. So you'll see that the atomic radius, notice, decreases as we go this way, which makes sense because we're going across a period. Atomic radius, atomic size, decreases. Notice there is no exception. 85, 77, it just cleanly decreases. But if you look at the ionization energy, notice there is an exception. Now the exception, if you take a look, is 801 to 1086, 14, and then down. So we're increasing, and then all of a sudden we have a break right here. We have a discontinuity. And that break occurs between oxygen and nitrogen right here. So it's like we're increasing in ionization energy, and we go down, and then we keep increasing. That's kind of how the trend goes. And so we have to explain that. The question is why? Why is this discontinuity happening? And the answer is due to oxygen and nitrogen. So let's look at the answers. A says the atomic radius of oxygen is greater than the atomic radius of fluorine. It's true that oxygen is bigger than fluorine because it's more toward the left, but that's not what explains it. It doesn't explain that discontinuity. Size itself does not explain it. B says the atomic radius of oxygen is less than the atomic radius of nitrogen. This is actually wrong. Oxygen is bigger than nitrogen. There are no exceptions to the atomic radius trend, so that one's out. C says there is repulsion between paired electrons in oxygen's 2p orbital, and then D is very similar, says there is attraction between paired electrons in oxygen's 2p orbital. Okay, so it's all about oxygen's 2p orbital. So if you take a look at at oxygen, here's oxygen's orbital diagram. Oxygen has 6 electrons altogether, so, but only 4 in the P, wait a minute, I apologize. This is a classical mistake. I just swapped oxygen and nitrogen. If you caught that, congratulations. This is nitrogen, this is oxygen. Which means the atomic radius of oxygen is less than the atomic radius of nitrogen was correct, but it doesn't explain the trend. Wait a minute. Apologize. Yeah, oxygen should have 4, 6 total. valence and 4 in the p. So, all right. So 1, 2, 3, 4, which means there is an extra electron in the orbitals. Remember that these right here are orbitals. And this extra electron creates repulsion. Electrons are all negative, so they will repel each other. So this is why oxygen wants to remove this electron. That's why oxygen's ionization energy is lower. It's more willing to remove that electron. Ionization energy is a measure of how strongly it holds on to the electron. So oxygen says, I'll let it go, more likely than nitrogen, because of this repulsion of the extra electron. So the best answer is actually C. So apologize for that slight little mistake. But in general then, let's take a look in general. If you were to explain the, let me just pull this down a little bit, and then you can do this, you can practice this on number 32. If you were to explain the trend for ionization energy, so ionization energy in general increases as we go this way, increases. If you were to explain that, you have to explain it in terms of effective nuclear charge. So you always want to use this term, effective nuclear charge. That's how ionization energy increases. In other words, the number of protons increases, increases, and increases as you go toward the right. The number of electrons increase, but they're added to the same shell, so the atoms get smaller and smaller and smaller. So effective nuclear charge is what explains it. Incidentally, effective nuclear charge is constant as you go down. Because remember, the effective nuclear charge is the number of valence electrons, minus the number of core electrons. So the number of core electrons as you go down, valence electrons stays the same, and core electrons essentially so even though you get more core electrons, you get more protons. Actually, I'm sorry, it's effective nuclear charge, you subtract away the number of electrons and the protons, the atomic number. Screening electrons minus the number of protons. It's screening electrons, screening keys. But the idea is that made no sense. It's just remember that effective nuclear charge is constant because you're actually going down the shells. And actually, that's what explains, if you take a look, if you were to be asked why the size trend decreases as you go this way, you can also say size trend decreases because of effective nuclear charge. Effective nuclear charge explains why ionization energy increases and size decreases. But if you were to ask why size increases going down, what you would say is each time you're starting a new energy level, new energy levels. Start each time. And so the number of core electrons, which can be on the inside, in each case increase, which these are the screening electrons. So yes, you do get a stronger nuclear charge as well, but the number of screening electrons increases proportionately, and that's why your effective nuclear charge stays the same, essentially. And that's what I was trying to explain unsuccessfully. So try to think through these. Go ahead and do number 32 and a few other ones, and we'll take a look at some questions on right before our tests.